Go ahead and run this syntax for the descriptives. And as we can see, the score for Asians looks higher than all of the rest, and then Black and Hispanic seem to be around the same. So this is going to give us an idea of where the differences might lie, but of course, in order to find out significance, we need to continue with the test. So now with this syntax, we're going to explore the relationships between the independent variable and the dependent variable using box plots as visuals. And then, as you can see, the output is going to confirm what our descriptives told us. That is that Asians scored highest on the selection measure with a mean of about 9. And whites scored the second highest, and then blacks and Hispanics scored about the same, but lower than whites and Asians. This is also going to tell us about the spread of the data as well, and the variance within each group. So regarding the syntax, I use the box plot and the GG functions to form the charts. The labs function gives labels to the x and y axes for my variables, and the AES syntax is going to give the aesthetic to the variables within the data set that I specified. So now we can look at that same information for the variables of the IV and the covariate to get an idea of that. The output indicates that Asians scored highest on the IQ test, whites scored the second highest, and blacks and Hispanics scored the lowest, similar to the scores on the selection measure. As you can see, there's also a few outliers, especially within the white group. And since we would expect there to be a couple of those with consideration to the type of variable that we're using for the covariate, I'm going to keep them in the data. And the box plot will also tell us about the variance within the scores for each race. Specifically, blacks and Hispanics did not vary much on their IQ scores, but Asians did. So moving on, step 2 is to check the assumptions. So Levine's test is the first thing that we're going to test, and this is going to look at homogeneity of variance. This will indicate whether the variance in the dependent variable varies across the interaction between race and IQ. So let's run that. Okay, so as you can see, we don't have a significant p-value. So this demonstrates that the assumption of homogeneity of variance has been met because the p-value is not significant. So we can conclude that the variance in the selection measure scores did not significantly vary across the interaction between race and cognitive ability. So in other words, the variances for these data are very similar. If this assumption were to be violated, I would run a robust ANCOVA that allows for the analyzation of the data while violating assumptions. So moving on. Next, we're going to check the assumption of independence. We need to make sure that the covariate of IQ is independent of the IV of race. So in other words, is IQ roughly the same across all 4 levels of the IV, so across all 4 races? And we can test this by running just a regular ANOVA model with race as the IV and IQ as the outcome variable. And in regards to the syntax here, I named the model or specified the model as check independence model, used the ANOVA function, and then specified the variables that I wanted to look at, attached the data right here, and then the summary functions actually produce the output for that. Okay, so as we can see, we have a significant F value, which means the assumption has been violated at different levels of the IV actually at all. So there are several options that I could take here. The first option is that I could drop the covariate from the model and just stick to a regular ANOVA. The second option is that I could ignore the violation of this assumption and continue with the analysis as if it weren't violated. The third option is that I could categorize IQ in high and low sections and then run an ANOVA. The fourth option is to enter into the bottomless pit of despair that Andy talks about in the book whenever you violate this assumption. So for the purposes of this, I'm actually going to choose option 2. I'm going to ignore the violation, and the reason that I'm going to do that is because I didn't have an experimental design. I had naturally occurring categorical predictor variables, so I'm really less inclined to be concerned about this violation. Keeping the covariate in the model is going to give me an accurate picture of the true relationship present. If I were doing an experiment, however, I may go for option 1 or 3, which is either dropping the covariate or categorizing IQ in high and low sections. Because the violation of this assumption in a design like that would indicate an inaccurate representation of relationships between actual effects of race and the selection scores. So, step 3 is to form the ANCOVA model. So here I've created Helmert contrast to compare whites and Asians and contrast to compare Hispanics and blacks. I'm mostly doing this for purposes of demonstration. I would likely only run post hocs in this specific scenario because I don't really expect differences across my selection measure scores if I design the selection measure well. To use type 3 sums of squares, we must specify orthogonal contrast because non-orthogonal is the default in R, and orthogonal contrasts are needed to calculate type 3 sum of squares correctly. So the first line of code here is going to set the contrast for the independent variable of race. The second line is going to create the ANCOVA model, and the third line is going to actually print the model summary. So we'll go ahead and run that. Alright, so from the output we can see that the covariate of IQ does not significantly predict the dependent variable of performance on the selection measure. The p-value is not significant. So another way to say that would be a person's IQ does not affect performance on the selection measure, and IQ is not a significant covariate. Which I kind of wanted it to be, but I guess that I didn't enter the data well to reflect that, so it kind of complicated things from here on out. But the performance score is not dependent upon someone's IQ, and I think that in real life it definitely would be. So I'm not sure what I did wrong, but anyways, there is a main effect of race on the scores on the selection measure. As we can see, the p-value is very significant. So that being said, if my covariate were significant, I would execute the following. I would get the adjusted means because the original means really don't tell us much about the differences between the levels of the independent variable, and the group means need to be adjusted for the effect of the covariates. So within this syntax here, the effect function is used to get the adjusted means. And again, the adjusted means are going to be examined if the f-test demonstrates that significant relationships exist between the covariate and the dependent variable. So a comparison of the original and adjusted group means can provide insight into the role that the covariate plays in this relationship. The SE means standard error, and the summary function is going to give the output of the code that we created for the adjusted means. So let's go ahead and run that. All right, so in theory, the output is telling me that Asians scored the highest, followed by whites, blacks, and then Hispanics. Again, this output would be more useful if I had a significant covariate. We might see more different numbers here between the means, or differences here between the means whenever we control for the effect of IQ, but IQ didn't have an effect again, so... So this would give me information regarding what the means of the groups look like when we adjust for the effect of IQ. All right, so step 4 is to compute the contrast specified and or do post hocs. So let's use this syntax to give the output of the model that we specified earlier. And again, we can see that the covariate is not significant here, but if it were, then I would look at the B values over here in this column in order to see which direction the relationship goes between the CV and the dependent variable. So for the IV, we can see that being white significantly predicts scores on the selection measure, as well as being Hispanic. However, in real life, I would probably run the post hocs after I saw the significant F value of race on performance, and if it had a significant covariate, because I didn't have any preconceived notions about which groups would differ. So regarding this syntax down here, to get the output of the model that we specified with the contrast earlier, we have to use the GLHT code. That's the one that we use to compare adjusted means. I specified Tukey post hoc because we are limited in our choices of post hocs due to the fact that we can only use certain functions here for adjusting means. So within this code, I'm specifying the variable as post hocs and using the summary function to get the actual output. The confint function will give us the confidence intervals, this one right here. So let's go ahead and run that. Okay, so the output is giving us the standard error associated with the difference between adjusted means, the t-test, and also its associated p-value. The output is telling us that there are significant differences between scores of blacks, whites, Hispanics and whites, Asians and Asians and whites, Asians and blacks, and Asians and Hispanics. There are no differences between Hispanics and blacks. So next we are going to examine some plots. The AOV function automatically generates plots we can use to test assumptions. So in the syntax here, I'm plotting the ANCOVA model in order to get visuals of the model that we specified. So all right, so the residuals versus fitted plot can test for the homogeneity of variance. You wouldn't want to see a funnel here. My data is super weird because I didn't have like a manipulation, so this graph is just very off. And then we also have the normal QQ plot. It doesn't look like I really violated it too bad, normality, so that's good. And